Okay, in this lecture video, we're going to look at some mechanisms, some general descriptions of the active transport process. So we said passive transport in our last video was movement down an electrochemical gradient, so it's natural, flowing from high charge or opposite charges together and high concentration to low concentration. So that does not require energy. But in active transport, we're talking about movement against the gradient. So for example, trying to move solutes from a region of low concentration to high concentration. So this is going to be an energetically unfavorable process, which means it has to be coupled to another process that will yield the energy for the active transport to happen. So some examples of those types of processes that active transport is coupled to, it could be the breakdown of ATP, which is our chemical storage facility for energy. So we could harvest some energy from ATP and use that to move a solute against its gradient. Or it could be flow of some other solute down its gradient. So if you have a solute moving from a region of high concentration to low concentration, that will reduce the chemical potential there, and that difference in energy can be harvested to move a separate solute against its gradient. So you can break active transport up into two kinds. The first kind is primary active transport, and that is directly coupled. So in this case, the energy producing process, whatever that transport is coupled to, so the energy producing or yielding process is used to drive, and we call it uphill transport, so going against the gradient. So for example, you hydrolyze ATP, harvest the energy, and move a solute against the gradient. The second type of active transport is secondary, and in this we have a little bit of sort of indirect coupling of the transport. So in this process, we'll take two solutes, A and B. So solute A is pumped against its gradient, using primary active transport. Okay, so that would be an example of what I just said. So for example, your membrane transporter hydrolyzes ATP, and you harvest that energy for that transporter to move a solute against its gradient. That would be the primary active transport. But that would be this first process here. And in the second step, the exergonic transport of that same solute, so of solute A down its gradient, is used to pump B uphill. Right, so now you've built up this chemical or electrochemical potential of solute A, moving it against its gradient. And now when it flows back down its gradient, that energy from it moving to a lower potential, so it's exergonic, it's freeing up energy, Gibbs free energy, that energy now is used to take a second solute, solute B, and pump it against its gradient. So in our examples that the groups are going to be showing, we'll see examples of all of these different types of transport mechanisms. So the amount of energy, or delta G, that it takes for these transport process depends on how steep the hill is, right? So how big is that electrochemical gradient? So let's take a simple chemical process, right? So if we've got some chemical process of A turning into B, we know that we could write the free energy, the delta G of that process. It would be the standard free energy plus RT natural log of Q, where Q is the reaction quotient. So it would be the standard free energy plus RT natural log of whatever the real concentrations are. Because we know, so I'll put initial here, we know that delta G naught delta G naught is equal to minus RT natural log K, where K is the equilibrium conditions. So K equals the concentration of B at equilibrium divided by the concentration of A at equilibrium. So our second term here for our real delta G takes whatever the standard delta G is and tweaks it based on what the starting concentrations are. So in the calculation of delta G naught, we're assuming that those starting concentrations are 1 molar. So our second term here accounts for the fact that they're not. Okay, so this is for some chemical process. When we're talking about transport, A and B are the same molecule. So in in the transport mechanism, A and B are the same. We're just moving a solute from one side of the membrane to the other. So since they're the same, delta G naught is equal to 0. There's no bond changes taking place overall. So that means we can write a new equation for the free energy of transport. So delta G for the transport of some molecule A across the cell membrane, it doesn't matter what direction you're going, is RT natural log concentration of A at the end, so final, divided by concentration of A initial. And this is for an uncharged solute A. So there's no charge on this. So we haven't accounted yet for any electrical gradients that we might have. Okay, so let's do that right now. And I'll go through in an example video how you plug in these concentrations. Okay, so if we're talking about ion transport, on the other hand, now we've got to deal with a chemical potential as well as a charge potential. So we're talking about some ion, let's make it a cation, starting on one side of the membrane and ending up on the other side of the membrane. So we can write an equation for delta G of the ion transport, and that's going to be RT natural log concentration final divided by concentration initial. So this part, this component, this deals with our concentration gradient. But now we're going to have another term that will deal with our electrical potential. So ZF, we're going to use delta pitchfork, which is also VM. So this is our charge gradient, so our electrical potential. So Z here, this is the charge on the solute. So for example, if it was a sodium cation, the charge would be +1. If it was a chloride anion, the charge would be -1. F here, that's Faraday's constant. That's 96,480 joules per volt mole. So that's the constant for moving a charge. And like I said, the pitchfork, delta pitchfork, that is our transmembrane potential, so you could use either representation. So utilizing this free energy, we can find out that many cells can actually create tenfold concentration differences using these active transport mechanisms. So I'm going to do an example problem in the next video, sort of give you an idea about how you would figure out what to plug in for all of these terms.